Scientific consideration of harmony. Of course, harmony from music, I mean. We can agree that many of you listen to various kinds of music, especially Western music or other sorts of pop music, etc. Each of such songs has the main melodies, the counter melodies, the bass, the riffs, and every such melodic part consists of 12 tones, do, re, mi, fa, sol, la, si, or ti, and also the black keys on the piano. Hum a part of the melody of your favorite song. You would notice that you could distinguish that song even without lyrics. What helps you to do so is, of course, the array of tones. So have you ever wondered how you tell what tune you hear? You were able to hum the melody without any notations, but you might not truly understand the mechanism to do that, because you do that too spontaneously. Here is an abstract answer. You hear them by the value of frequency of the sound wave you hear. The higher the value gets, the higher the sound would be heard. From the medieval, or much older period, philosophers and musicians decided to name such notes. Pythagoras is now said to have first established the idea to define each distance between tones. He found that we can make a system of all 12 tones by a very simple ratio between two frequencies, 2 to 3. These days, we have many other ways to define all of 12 tones, and we call the sequences of such ratios of frequencies intonation or temperament. Now let's focus on two intonations, equal temperament and just intonation. In equal temperament, every half step has exponentially equal distance. This is useful to tune the piano, for many piano pieces include hectic modulations. However, defined unnaturally, this temperament is said to be harmonically distorted. Just intonation is defined in greatly simple ratios of frequencies. It is even more simple than the Pythagorean tuning. And it is said that tones with just intonation harmonizes well due to its simplicity, where I doubt it. I mean, how can you tell that 32 versus 45, that is C versus F sharp, simple? So here's the question of my research. How do I make better harmony? I set my goal to define the concrete values of the best harmonizing intonation. Now, I want you to make sure that I'm not trying to impose a selfish idea about what is the best music or something, because it gets more controversial and it is not essential. What I focused on is only about harmony. I think the essential value of this research is that we can discuss harmony theoretically and simply understandably with a little bit of mathematical knowledge. This way of thinking may also contribute to contemporary live music or computer music, despite thinking relying on a traditional way. To continue my research, I needed a numerical way to evaluate harmonies. And when we talk about harmony, we need to think about the combination of multiple sounds. Then I came up with an idea, which I call the harmony level. Suppose we evaluate two sound waves, the one with the blue wave in the top left and the red one in the top right. Each period of the sound wave is shown with the green mountains and the purple bowls. When we put these two waves and marks of periods, we get this seemingly complicating figure in the bottom left. This figure itself doesn't make sense, so let me extract only the period mountains and bowls, just as shown in the bottom right. Now it is quite obvious that it takes two green mountains or three purple bowls to firstly meet the common end of the units of each wave. Generally, when it takes a shorter time to meet the common end, the frequency ratio is more simple, and that shows it's a better harmony. It seems like counting how many periods of the root sound the very single main sound of a whole chord we need to meet the common end of all composing sounds, can be the first step of defining harmony level. That harmony level should be increasing, while the harmony gets better, of course. Counting periods to meet the end is the opposite. The number of periods decreases when the harmony gets better. How can we fix this contradiction? Maybe inverse can help. And that's the main idea of the harmony level. When we write the value of the harmony level in a formula, it would look like this. Divide the period of the root sound by the least common multiple of all the periods of the composing sounds of the chord. Multiply it by 100 to make it handy, and you get the harmony level. Once I could get defining the harmony level, I thought maybe I can improve the best harmonizing intonation by evaluating chords with this value. And I did, and I was successful to suggest a better intonation in harmony than just intonation. Here are some of the chords I evaluated by comparing the value of the harmony level. The harmony level of a major chord, C, E, G, is 25%, both in just intonation and the new intonation I suggest. The harmony level of a minor chord, C, E flat, G, is 10%, also in both intonations. The diminished seventh, C, E flat, F sharp, A, is one of the biggest advances I made to define the new intonation. In just intonation, the harmony level is 0.2083%, while it is 6.6667% in the new intonation. Here I show you the keyboard of a whole octave. Each key is written on the frequency in just intonation, supposing the root is C and the frequency of C is 1. Stare at it for a while. And here is the same keyboard, but in the new intonation. It is quite similar to just intonation, of course, but look at C sharp and A sharp. These two have some options to choose from, and which one to choose depends on the chord. Maybe there's more tone we should give multiple options in these 12. I need more samples, I guess. Future initiatives. I know I haven't reached the musical topics, but physical or mathematical. Once I complete examining all the samples I need, I will possibly work in thinking about the way to realize this theory into live music, namely the orchestra. Also, for those who enjoy contemporary music, I hope it is possible to do the same evaluation and define the best harmonizing microtonal intonation. Thank you for listening and enjoy the music.